That legendary place that the end of the map reveals. It's only legendary till someone proves it real. Okay, we're looking at a practice problem here for projectile motion. And what we have in this problem is our pirate friends questing for the One Piece. They fire a cannonball at 125 meters per second horizontally at a height of 17.5 meters above the ocean surface. And I kind of drew the ocean surface wavy here, but maybe it's better if we draw the ocean surface as just a flat line. We're going to ignore air resistance as always. And we want two things here. How much time elapses until it splashes in the water, and then how far from the ship does it land. So if I kind of like finish my drawing here, you know, we've got like a cannonball thing, cannon, right? And when it fires, fire, it's gonna thunk into the water. And that's a bad curve. You know, we know this is gonna do something like that. Splash, splash, and you know, the water, you know, oh cool. Okay. So what do we want to do here? Well, we always come back to the box. We know in the box if we have 2 out of 3 things, the 3 things being velocity is 1, a delta x is 2, and a time is 3, we're good. We're good to go. Remember, the acceleration equals 0 in the x direction because once you shoot the cannon off, nothing's pushing it anymore. And in the y direction, if we ever have 3 out of the 5 things over here, we can call our best friend for help. Okay? So what do we have right now? Well, we know the ship fires the cannonball 125 meters per second horizontally. That actually gives us 2 things. First, it gives us the initial velocity. It lets us know that, hey, look, our velocities here are 125 meters per second. And in the x direction, the initial velocity equals the final velocity because there's no acceleration. So we know these are 125 meters per second. We also know because of this that if we shoot this horizontally, the cannon isn't being shot up at all, it's not being shot down at all in the y direction. This means the initial y component is 0. Okay? What else do we know? We know it's shooting at a height of 17.5 meters above the ocean surface. So we know that this distance here is 17.5 meters. So when the cannon falls, or the cannonball falls, we know it's changing its displacement by 17.5 meters in the negative direction. So that's 2 things we know. And what else do we know here? Well, what's causing it to fall? Oh yeah, that's gravity. That's our 9.8 meters per second squared. And if we're calling down negative for the delta x, you better bet that gravity is negative acting down as well. Okay, so our little picture here in our box allowed us to get that. And if we look at it, we've got 1, 2, 3 things for me. And that means we can use our best friend. If we want to find time here, we've got these 3 things. We want to find time. This is actually going to be very similar to our baseball problem we just did. If we go to our best friend, we could quickly see equation number 5 is what we want, which is delta x equals, and when I say delta x here, I just mean displacement. Some people like to write this, in our case, as delta y, because we're on the y side of things and it's moving up and down. But I'm just saying delta x is a general displacement. In our case, we're talking about up and down for the y side of the problem. If we were on the x side, we're talking about the x side of things. Okay? So a displacement here is equal to an initial velocity in the y direction, right? Because we're in the y direction, multiplied by time plus 1/2 times the acceleration in the y direction, or gravity, times t squared. And if we go ahead and throw in some numbers here, we're going to get negative 17.5 meters equals, well, 0 times the time is 0 because our initial velocity is 0. So this is just 0. And then plus 1/2 times the negative 9.8 multiplied by t squared. And at this point, it's just some algebra. In the baseball problem, I like to multiply the 1/2 and negative 9.8 together. So I get negative 17.5 equals negative 4.9 t squared. It's just like how I like to do my math. You know, if you want to multiply by 2, then divide by negative 9.8, whatever. But then we divide by the negative 4.9, divide by the negative 4.9. Something you will notice here is that our negatives do divide out. If you find the negatives don't divide out and you say that time squared equals a negative number, when you try to take the square root of the negative, it's going to give you a non-real answer, and your calculator might, explode in your hands. That's because you just got an imaginary number, and that's not allowed. So, well, it's not allowed in the physical sense of shooting cannonballs here. So make sure that those negatives divide out, and that's just because you need to remember that, both of these are negatives here. What is 17.5 divided by 4.9? 17.5 divided by 4.9 gives us 3.57, and that is times the time squared. And if we want to get rid of that squared, we simply take the root of each side so that we find the time is just the square root of 3.57. So the square root of that 3.57 is just about 1.89 seconds. Okay, so that's our answer to part A right there. So let's go back up to the box and let's put in that our time is 1.89 seconds. Now, if we have the time here, that's how long it took the cannonball to fall, but it's also the amount of time it took the cannonball to move over because it hits at this point at the very end. So that means this time can jump to the other side, and that this here in blue now becomes a 1.89 seconds as well. And the great thing about that, since they share the time, now we have two things on the left side. We've got a velocity and we've got a time. We can solve the delta x. We can figure out how far from the ship the cannonball landed. To do that, on the left side here, we always are just using equation 1 because the acceleration is 0. And if we use equation 1 here, we find that equation 1 is velocity equals delta x divided by time. If we're solving for how far or the delta x, we can just say that delta x equals the velocity multiplied by the time, which will just be 125 meters per second multiplied by 1.89 seconds. We see that the seconds easily cancel out here or divide out. And 125 times 1.89 is, that's a pretty big number. Our delta x here is 236.25 meters. And that's it. That's our answer for how far the cannonball went. And if we wanted to, we could come back up here. We could put the 236.25 in here, and that's our box. Like I said in the last problem, we could, if we wanted to, solve for VF, but we didn't need it in this problem. We weren't asked to solve it. We really didn't care. We just used the Y side and our best friend to figure something out. But that's it. That solves our entire problem, what we're looking for. We know how far it went. We know how long it took to hit the ground. We're finished. Okay? So with that, we solved a lot of things about projectile motion here. Once again, we have a horizontally shot object, so the initial y velocity is 0, and in this case, we happen to know the x velocities. So yeah, we just went through our best friend, did a little bit of algebra, and filled out our box, and that was it. So that problem is finished. In our next one, we're going to look at a battle tank. And instead of starting from the Y side of things and working to the X, we're going to start on the X side of things and then work over to the Y. But until next time, adios, and take it easy.